Greetings. In part A of this problem, we found out the properties, we defined the um, control volume or the system, we solved the problem, we drew the diagram, and now is the time to simplify conservation equation. Well, mass conservation tells us that the change of mass inside any control volume by time equals the rate the mass enters that control volume minus the rate that that mass leaves that control. Now, integrating this between any initial and final conditions in this problem, you see there is no mass entering and there is no mass leaving, and therefore what we would get is that m2 minus m1 equals 0. Well, that's the conclusion I made initially when I said that when it's a rigid volume, nothing comes in, nothing goes out, and m is constant. But this is a more uh, technical thermodynamic way of concluding that initial and final mass are the same. Now, we could change this and write it like this: V2 over V2 minus V1 over V1 equals 0. Mass equals volume divided by a specific volume. Now, since V2 equals V1, since it's a rigid tank, therefore V2 equals V1. It means that in both cases, case A and case B, the final specific volume equals the initial specific volume. Well, that's a very interesting conclusion. Let's draw it on our diagram. And what we see is this, that the process, our process for case A goes over this line, and this would be point 2 for case A. And for case B, it would be this one, and it would be case B. It is 2B. So we have two different processes, one from point A and one from point B. And mass conservation law told us that a specific volume remains constant. You see here, our specific volume, V1A, was 0.002. And here, our specific volume, V1B, was 0.2. And this is how we draw it. Of course, I don't know the position of points 2A and 2B, but shortly I will find out what the different properties of point 2 and point B, point 2 for A and B are, and whether I have drawn this correctly or not. You see, for point 2A, what do we know about point 2A? We know that x equals 0. And we know x equals 0 because point 2A is just before the critical point. So it would be on the saturated liquid line. X equals 0, and V2A equals 0.002. These are two properties that we know for point 2A, and for point 2B, we know that x equals 1, since the problem told us that we heat it so that either we have liquid or vapor. And in point 1A, we would end up as liquid. In point 1B, we end up with point 2B as vapor. And V2B equals centimeters per kilogram. And therefore, we have uh, we have two processes. We know two properties for each final point, and all we need to do is to go to the table, and see on the saturated liquid line where the specific uh, a specific volume is 0.002, and that's where the point we want. Again, we have to go to the saturated vapor line and see where on it the specific volume is zero point 0.2, and that is exactly the point that we are looking for. So that's what we are going to do right now. Well, this is again our table, and um, here is VF, and these are all specific volumes for saturated liquids. These are all specific volumes for saturated vapor. These are all specific volumes for saturated liquid. These are specific volumes for this line, and these are specific volumes for this line. So here for point 2a, we have to look at the specific volumes here, and if we keep going down, we would see that there is one point where a specific volume is 0.002015, which is a good approximation. So the conclusion I would make here is that for point 2a, I would conclude that T2a equals, just from this table and from here, T2a is 365 degrees C, and P2a is pressure, P2a is 19.822 megapascals. You see, we are very close to critical point, which is here. Critical point is here. We are very close to it, and the temperature is very close. We are only less than 10 degrees, or something about 9 degrees away from the critical point, and the pressure is only 3 just more than 2 megapascals away from the critical point. So point 2a is very close to the critical point. Now, what you should do here is to go to this column, the columns for a specific volume at saturated vapor line, which is this column, the VG column, and see where our specific volume is 0.2. And if we just keep going up, you would see that 0.2 happens somewhere between 175 and 180. This is 0.19384, and this is 0.21659. It's somewhere between these two, and by some interpolation, we would get that T2B equals 178.6 degrees C. You see, although it looks with my poor drawing that these 2 points have the same temperature, but in reality, this is wrong. This point would be far lower. It would have been better if I had drawn point 1b here, and point 2b would be here, and it would be much better representation of the problem. And P2b is 973 973 kilopascal, and that is P2B. So the pressure is far less. You see here the pressure was 19 megapascals, and here on 2B pressure is barely 1 megapascal. So if I had drawn point 1B here and point 2B here, then it was a better representation of this problem. And these are our final properties here. Now, before ending this problem here, which I've just calculated points 1 and point 2, and everything we know about this process, there's one more addition to it, which is good to know here, and that's what happens to energies. You see, for the initial point, we have 1A, and we could calculate its quality. There is a quality to it, and x1a would equal a specific volume V1a minus Vf and divided by Vg minus Vf. I'm putting numbers to it. That would be 0.002 minus 0.001012 divided by Vg minus Vf, which is Vfg, and we know it to be 12.025. And x1a would equal 8.2 times 10 to the minus 5. It's almost saturated liquid. There's not much difference from it. Now, what we did before is that we read specific energies for saturated liquid and saturated vapor, and we calculated the difference. Now, what we could calculate now here in the same manner as we do for uh, a specific volume, we could calculate the specific energy for point 1A. And U1A, it means the specific energy here is UF plus x1a times UFG, and that would equal UF, which is 209.33, plus x1a, which we just calculated it to be 8.2 times 10 to the minus 5, and times UFG, which we learned it to be 2233.4. And the outcome for U1A would be, for U1A, the outcome would be 209.51, very close. 209.51 kilojoules per kilogram, very close to UF. In a very similar manner, and I won't repeat it here, I will just give you the results, we would calculate for point 1B, x1B would equal 0. X1B would be 0.0165, and U1B would be 246.3. This is U1B, kilojoule per kilogram. So this point, this specific energy is 209.51, and for this point, this specific energy is 246.3. So we have two different points, we have energies for our initial conditions. Our energies for final conditions, you could read them from the table. So U2A would be 1777.2 kilojoule per kilogram, and U2 in case B here would be 2581.9 kilojoule per kilogram. Now, the point is very interesting here. The point is very interesting here. You see, the mass is the same. Okay, the mass is the same. We have heated it. We have heated it either to become a liquid or to become a vapor. Now, how much heat did we need? Of course, later on, first law would tell us that it is only heat. But let's see what the change in energy is. How much energy has changed in these two properties? And for property A, U2A minus U1A equals 1567.7 kilojoule per kilogram. This is the change in energy here. And for process B, U2B minus U1B equals 2335.6 kilojoule per kilogram. You see, the change of energy here is higher than the change of energy here. In both cases, we have increased temperature and we have increased pressure. The interesting point is that here we have increased temperature more, up to 365. We have increased pressure more, up to 19 megapascals. In this case, we haven't increased temperature as much as the previous one. The temperature has only increased 178 degrees. The pressure has only increased up to 1 megapascal. So what has happened? Why the change of energy here is far more than the change of energy here? And the reason is very simple. The reason is because the water here has vaporized. And the change of energy is because water, liquid water, in this case, is turning to vapor. And this is the vaporization energy that is absorbed here just to change this water to vapor. Here is only the temperature that has increased, but no liquid has turned to vapor. And this is the difference between these two cases. Although in this case, the temperature has increased more, the pressure has increased more, but since no liquid has turned to vapor, therefore it requires less energy. Here, the temperature has increased less, the pressure has increased less, but since liquid has turned to vapor, it requires more energy. Thanks very much for watching and cheers.